So I'm not an astrophysicist, nor am I a biologist. Purely technically, I am an oceanographer or a biogeochemist, but I also answer to astrobiologists, and I think that interdisciplinary perspective is going to help frame the way I talk about geochemistry or biogeochemistry. And before I forget, I want to thank the Sagan workshop organizers for inviting me. I have to call out Natalie Hinkle, who I don't have a picture of, but she is a key player in one part of this talk, the hydrothermal organic geochemistry group at ASU, and my own lab, the carbon and nitrogen dynamics lab. So none of this happens and none of the thinking happens by myself. I have to have teams of people around me. So there's some of them. So what do we know about exoplanet biogeochemistry? And if you listen to all the talks for the last 2 days, you might think we know a lot. But in reality, what do we know? We know almost nothing. And we are still limited by 3 things: theory, models, and data. And this is with apologies to everybody who's doing spectacularly good theory work. We really do have ideas about how things work. And we are getting to the point where we have much better models. So I'm going to make the argument that our models are not well integrated across kind of classes of models yet. And as far as exoplanets go, data is hard, right? We are a highly data limited field because we don't barely have pictures of exoplanets, let alone spectra of exoplanets. But I am undeterred by this problem. So what do we need to know? Well, we need to know this. I am so glad you guys laughed. And I can't tell you about all of this today, but I can pick out a few things on this list that we might know enough about to begin to look at something. And so I'm going to focus on stellar compositions. You will hear things about thermodynamics later on in this talk. I will mention things you've heard before, like photosynthesis and respiration and nutrients. I'm going to throw in a little hydrology and some organic chemistry. But these are aspects of biogeochemical cycling or geochemical cycling that we may be able to make progress on sooner rather than later. So our Earth is beautiful, and this is my shout out to the Apollo mission. This is an Apollo picture of the Earth from Apollo 11. So it's not a new picture, it still looks nice. But our Earth is an inhabited Earth, right? We can't talk about our Earth without talking about the intersection of the geosphere, the hydrosphere, the wet part, the atmosphere, which may or may not be part of the hydrosphere, depending on who you are. And the biosphere sits at the intersection of those things and can't be pulled apart from them. So what do you need to know at the end of this talk? First thing you need to know at the end of this talk, phosphorus and nitrogen are critical for biogeochemistry, and we know almost nothing about them in stars and even less about them in planets. Second thing you will know at the end of this talk, biogeochemistry on planets with more water than Earth and less water than Earth will be hard to predict. And we are going to have to be more creative about the way we think about geochemical information and where we get it and how we're going to interpret it. So how do we get there? I'm going to talk to you about elements in stars and planets. I'm going to make a case for ecosystem ecology and a plea for these more integrated models because we're talking about emergent properties and not individual compounds or individual organisms. And I'm going to hopefully have time to go through 3 very short vignettes about different types of exoplanets. So, elements in stars and planets. If we look to our own solar system, our planets have different compositions. We know that, right? The Earth has water and rocks and life, and we just heard that something like 50 or 60 of the elements in the periodic table are needed to account for things in living systems. We know about gas giants to a certain extent, and we go, oh yeah, they're hydrogen and helium, and they probably have the rest of the periodic table, but we can't really measure it very well. And we heard just in the last talk, Kevin told us about icy bodies, and we know that they have water, and they probably have rocky cores, and some of them have organic compounds in their atmospheres. And we presume that exoplanets have all of these kinds of characteristics, plus a whole lot more that we don't know what they're going to look like. So if we don't have examples in our solar system, how are we going to imagine what those planets look like? What are their compositions? Well, we generally presume that planets will look like their stars, right? People have heard this before. If we know the stellar composition, we can say something about the planet composition. Let's unpack that a little bit, just a little. I don't disagree with it, but it's challenging. Fortunately, my colleague Natalie has the Hypatia Catalog. Hypatia is the largest catalog of stellar abundances for nearby stars. And I was told by Natalie, you have to say what nearby means. Nearby means within 150 parsecs. So it's not like they're across the street, but relatively speaking, they're nearby. And this catalog is awesome, and you can go to hypatiacatalog.com and you can play with it and find out all kinds of stuff. And what it is it's a database of the elemental abundances that have been measured in these stars. And here's a histogram. And this is basically numbers of stars with a measured composition. And it's about 73 of the elements in the periodic table. There's 6,200 stars in it right now. All of the ones that are in here have data for iron and at least one other element. Some of them are rock-forming elements, silica, calcium, iron, and thousands of stars have these data. Some of them are rock-forming elements for which there's not very many stars that have data. Some of them are these elements that are important for life, right? The carbon, nitrogen, phosphorus that we've heard about several times in the context of the redox or the Redfield ratio. And if you're carbon, you're all right. There's 4,000 stars. There's 1,500 stars with nitrogen data. And then this is where this all started. I said, Natalie, how much phosphorus is there in stars? And she kind of looked a little sheepish, and she's like, there's only 92 stars with phosphorus data. Phosphorus is hard to measure in stars, it turns out. The line is out somewhere around a micron. It's complicated by water and overlapping bands. And so, yeah, I get it. It's a mess. But if you're a biogeochemist, we have to solve this problem. Why? Well, because we get to this problem of life cares about phosphorus, right? We have lots of compositions of life, right? We can simplify a little. Remember photosynthesis, which we heard, all about from Bob and from various other people who talk about the process that involves oxygen. It has a fairly fixed stoichiometry, a fairly fixed ratio of elements in moles. You need 106 carbons, 16 nitrates, 1 phosphate, some water, and some protons to make this more complicated version of the organic matter simplification. It's still a sugar, but it has 106 carbons, 16 nitrogens, and 1 phosphorus. Phosphorus, in this case, the phosphate, is the limiting reagent. So here's our plankton. Whoops, and I'm going to mess this up again. And it has that 106 to 16 to 1 ratio, but we can compare this to other things we know. The Earth's crust has a ratio in this same arrangement of 5 carbons to about 0.05 nitrogens to 1 phosphorus. And the sun, to the best of our knowledge, has a ratio that looks like this, about 2,550 to 1. Plankton, the Earth, and the sun, from a molar ratio standpoint of carbon, nitrogen, phosphorus, don't look anything like each other. So this planets look like they're stars thing could be problematic. Now, in the interest of full geological disclosure, it's only the crust, and our Earth has happily fractionated and differentiated itself, so a lot of the elements are not in the crust, they're in the core, for instance. But we're not going to worry too much about that. What does the Hypatia Catalog tell us about other stars? So here's Hypatia Catalog data. What I've plotted is nitrogen to silicon ratio and carbon to silicon ratio, and all of these symbols are stars, and if they're black, they're stars that have a known exoplanet. And there's a lot of data, right? 1,400 stars have all 3 of these elements, nitrogen, carbon, and silicon, and there's a pretty good blob right here. And these histograms are sort of relative distributions, which says that most of them have a ratio kind of like this in the carbon-silicon space, and most of them have a ratio kind of like this in the nitrogen-silicon side of things. And here's our sun. It's not in the blob. And here's our Earth's crust. Comparatively speaking, it doesn't have any nitrogen and carbon. And here's life. right? Plankton. I think it's strangely interesting that plankton looks a little bit more like stars than our Earth does. But this is just asking the simple question, what's the distribution of these elements? And these are molar ratios. So for the astrophysicists in the room, we actually had to take the abundance information, decide something about that hydrogen normalization, and calculate numbers of moles. So this isn't necessarily the amounts that you're used to looking at. I am unafraid to go all the way to phosphorus. And then all of a sudden you have that problem of there's not any stars. And of the 90 stars with phosphorus, only 50 of them also have nitrogen and carbon data. So we have the problem that we don't measure all the elements in the same stars. Well, now, what do we see? Well, we see, first off, there's hardly any data. That's the main take-home message from this part of the story. What data there is says that C to P ratios in stars is something between 500 and 1,000, and C to N ratios in stars is something like 5. Well, there's our sun, still looking not like most of the stars in the Hypatia Catalog. Could be due to the fact that the way we measure stuff in the sun isn't necessarily the same as the way we get it for the stars in the Hypatia Catalog. It could mean the sun is actually weird. Here's our Earth's crust again, and here's phytoplankton as the example of all life. So really the thing to know is that we know something about compositions of stars. We know a lot less about how to determine the compositions of exoplanets. And if we're going to think about where life fits into the compositions of planets or planet crusts, we're going to have ways to actually distribute elements into those planets and then partition them the way planets actually partition, right? We're going to have to do planetary differentiation and geochemistry to figure this out. So to summarize this section, molar ratios are important, and we need molar ratios because we're really all chemists. You don't know that, but we're all chemists. And it's important for making rocks. It's important for biology because those are chemical reactions. We also need to predict planet compositions from those stellar compositions, but we don't have all the elements we need. And we don't have good models for how to do it. We're getting there. But that's a big thing we need to work on as exoplanet people. And we really need phosphorus data. We really need phosphorus data. You're about to hear a theme through my talk is that I'm going to complain about phosphorus the entire time. Okay, so elements in stars are a key thing we need to know about, and there are certain elements for which we have very little data, in particular phosphorus. But there were other elements up there that were important for rocks or for life that we don't have very much data for. So we still need good information about this. Geochemistry, or geobiochemistry, or biogeochemistry, depending on where you want to emphasize your frame of reference. It turns out, Craig Manning said at one point recently, the biochemistry we have is the one the Earth allows. We need to remember that thermodynamics, kinetics, the geochemistry of the planet is very tightly coupled to biology and biochemistry. Our planet and our biosphere evolve together, and those biochemical processes have geochemical origins. If a planet has a different composition, redox, temperature distribution from the Earth, it could have a different biochemistry. Now that's a kind of an out there statement, and I'm not going to talk about different biochemistries, but it's just worth remembering that our biochemistry is tightly coupled to the geochemistry of our planet. So what does that mean? We just have to explain this, right? We have to be able to explain how you go from some hot, melty Earth, like, you know, during the magma ocean, to this. Well, when you go from the hot, melty Earth to the early anoxic Earth, which we've heard quite a bit about in the early parts of this workshop, we know that water, rock, and biology reactions likely have to slow down because the Earth is cooling. We know that we're making plates and continents, and that's also inherently related to the process of cooling the planet. But there is great debate about how all that works. But we do know that when those reactions are slow, there's still energy to be released in those reactions because they're thermodynamically favorable, and life catalyzes those slow reactions in order to get the energy it needs to do its thing. Unfortunately, we live over here, and we have very little evidence from the rock record for the early Earth. And the Earth has been contaminated by life for this entire time. And so asking what an abiotic Earth would look like, or what is the geochemical Earth, is virtually impossible. And so then saying we're going to ask the question what a geochemical exoplanet looks like, we're making our jobs harder. Oh, this is here to remind me that yes, all of these, and this is a variation of things you've seen before. Here's the geologic timescale, properly moving from left to right, going forwards. And this is when we thought the water evolved, way back when, evidence for isotopic evidence that might have been associated with life, fossils. Very uncertain, but basically old times of origin for metabolisms on Earth. The great oxidation event is also not linear time, sorry about that. And now, you know, animals and things like that. But the coevolution of life, the biosphere and the planet are really very well established for Earth. It's not like we made a planet and then a long time later we made life. So we need integrated models. And by integrated models, I mean models that address both the process of differentiating a mantle and a core, a process of making plates and plate tectonics, process of getting stuff from the mantle to the surface to the atmosphere and those kinds of things. And we don't really have those right now. I like the Winogradsky column analogy quite a bit. And I want to point out that I made all of these slides before I got to this meeting. So all these things I'm saying that everybody else talked about was very comforting. Many metabolisms are present in a Winogradsky column, like the ones we saw yesterday, from autotrophs to various types of heterotrophs. And if this one had a cap and you could measure the gas at the top, it would measure some integrated signal of all of those metabolisms, right? And of any abiotic processes that were happening in this Winogradsky column. So it's essentially a system scale measurement. It's a small system in this case, but you could think about it as a big system. So a systems perspective, or an ecosystems perspective, says that multiple metabolisms are going to co-occur, and we should assume this is true for other planets. It's brighter over here. And on Earth, biology so dominates the cycles of carbon, hydrogen, nitrogen, phosphorus, and sulfur that we often forget or ignore the geochemical side of things. And we've heard this before too. We have to remember that the geochemical processes are there. And for other planets, they could be much more important, or at least of a scale that's comparable to the biological processes. A systems perspective is not brand new, though we've got fancier names for it. These are my old white dudes. Charles Lyell. How many know about Lyell? Lyell's a geologist. He wrote this thing called Principles of Geology in 3 volumes. It was, at the time, the treatise on geology. And it is reputed that Charles Darwin took the 3 volumes of the Principles of Geology with him on the Beagle when he was exploring the great world that we didn't know so much about at the time. And remember, this is all happening in the 1800s. And so Darwin appreciated geology. Darwin understood that evolution happens in the context of the Earth that things are happening in. Vernadsky obviously knew all of this too. What it leads us to is the possibility that we should be thinking about a net planetary signal of whatever process it is we care about. It could be the production of oxygen, it could be the production of methane. And I am harvesting this concept from oceanography, the idea of net primary production, where primary production, or net primary production, is the balance between, say, oxygen produced by organisms and consumption of that oxygen by organisms that do respiration. But if you're going to do it for a whole planet, and that planet also has abiotic geochemical processes happening, then you have to add in the other part of the net. So you have the net biology part plus some net production and consumption due to geochemical processes. Okay. Simple enough, we could do that, right? It's also all premised on this idea of fluxes, a change in the concentration of something over time. often normalized to area, but we won't get into that. A flux is biogeochemistry in action. So the change in oxygen concentration over time is basically the balance between the sources of oxygen and the sinks for oxygen, and those sources could be biological, like photosynthesis, but they could be strictly abiotic, like photolysis and hydrogen escape. The sinks could be biological, like respiration, but they could also be these reductants that people have been talking about, iron sulfides and other reduced things. I'm going to run out of time. And those reductive sources come from the solid Earth, right? They have a fundamentally geochemical sort of storyline, and we often don't appreciate that. I was very pleased when, on the first day, someone was talking about this idea that Earth is like this planetary scale redox gradient. It's very interesting that all the iron, for the most part, is down here in the core, and it's all as iron 0. It's super reduced. And up at the crust, there's not very much of it, and it's iron 3. But it turns out that's 3 electron difference, and the amount of iron in the core could reduce the surface iron like 30 times over. Oh, and these colors, I love these colors. It turns out the blue and the green are actually the colors of the forms of olivine and ringwoodite that actually make up much of the upper and lower mantle. And so I decided to color it blue and green because it's always red and orange. And it's like, I like to think of the interior of the Earth as being this color. But what we really need is we need these models that are going to not only differentiate our planet and convect stuff through the mantle, but actually tell us how much is going to degas from a volcano, is going to tell us about weathering from the surface, is going to actually deal with serpentinization, or even biology, right? I've put those all 4 as equally valuable, coupled to models that do mantle dynamics and biogeochemistry and atmospheres. And that's a hard game. Not only is it computationally intensive, but the types of models that are tractable for, biogeochemical cycles don't necessarily talk to mantle convection models very well. It could be done, but we don't do it. So this is mistake number 1 in this talk. I'm going to put up a differential equation. Not a hard differential equation, and it's been one-dimensionalized and all that kind of stuff. But you could imagine a flux of a reductant being expressed, as a sum of all the species and stuff that you care about, as a diffusive source, an advective source, and a reaction term. There's the chemistry, and they have signs associated with them. So you could write this, say, for the gassing of sulfur for a volcano. Well, you need to know the magma composition, which sulfur species you care about. You'd have a passive degassing kind of mode and a magma ascent sort of eruptive mode. And maybe you have some reaction, though for sulfur, we might assume that that's not a big deal. But you could write a chemical reaction in this form. You could then plug it into whatever, forward geodynamical model you want. No problem. That was irony. And you could do it for all those other processes that I mentioned. I'm not going to show you all those equations. But these things are hard to measure. I'm not trying to downplay the difficulty of this. But if you walk through the solid Earth drivers for reductant flux that matter, you find out that things like continent mass matter for all of these processes, and that uplift and weathering matter, perhaps more for the biological and surface weathering kinds of processes than, say, for magmagenesis. And some of these processes actually stretch across all 4 of them. And so there are ways to start to say, okay, these are the more important things to worry about for building these integrated models. They don't have to be perfect, but they have to include these sorts of processes. I'm running out of time, and I haven't gotten my exoplanets. There's a lot of them, and many of them are likely to be in some concept of a habitable zone. We need this planetary production framework in order to begin to assess what we might see on an exoplanet, right? Because we're not going to see proteins, or genomes, or microbes. What we're going to see is the influence, maybe, of those microbes at a planet scale. And this equation might help us with that. For a water world, and this is a simulation of types of numbers of planets with different water contents relative to the Earth, bunch of Earth-like planets, many with more water than Earth, a lot more, a whole lot more, some with less water than Earth. And we presume that Earth is habitable, but we don't know if these are habitable. So here's a thought experiment, and this is based on the same kind of oxygen cycle that Jen Glass showed us. And most of the numbers in this come out of Catlink's 2004 paper, but the upshot is we outgas stuff from volcanoes, we weather stuff off of rocks, photosynthesis and respiration are turning over at a large rate of something like 10 to the 4th teramoles per year, a little tiny bit of photolysis, and the net oxygen production, when you bury a bunch of reduced stuff, is about 17 to 20 teramoles of oxygen per year. Great. What happens if you have way more water? Well, okay, we're going to assume 5 oceans of water, and we're going to bury the continents. We're going to assume that everything about those continents is just like they are on Earth. Really hard. Anyway, what's going to happen is that the weathering flux, this weathering of stuff off of continents, is going to basically tank. And that means the supply of stuff to the ocean from weathering, i.e. nutrients, is going to go down. Why? Well, it comes back to our friend phosphorus. Apatite is the main phosphorus-bearing mineral. It's an igneous rock. Sometimes you find it in this beautiful gemmy blue quality. It's a problematic igneous rock because many of the models that are doing planet differentiation and subduction zone chemistry and things like that, they don't actually explicitly use apatite as one of their mineral phases. Apatite's also super stable. It degrades very slowly. Best estimates for the solubility product, how much of it dissolves relative to how much of it doesn't in water as a function of temperature. These are log K values of -43 to -116. That's 10 to the -116 in whatever dissolution units you want. It doesn't dissolve very fast. So you have to weather it into tiny pieces, and you have to get lucky. And on Earth, the weathering supply of phosphorus is about 0.07 teramoles per year right now. But if you don't have weathering on continents, you only get weathering of those submerged continents by some sluggish seafloor current or something. You don't get much phosphorus. And we estimate that that phosphorus flux on a water world, with just the 5 oceans of water, is like 400 times smaller. You might only get 0.00016 teramoles per year. And if you have an ice mantle that's separating your seafloor from your ocean, you maybe don't get any weathering at all. You also maybe get more weathering. This is highly unconstrained. But the end game is that on a water world where your continents are covered with water, your photosynthesis and respiration rates are going to be strongly limited by the fact that there's no phosphorus supplying, and you're going to get way less than 10 to the -4 teramoles per year, which means by our estimates, you might only get 0.01 or 0.02 teramoles per year, and now it's about comparable to the photolysis rate. So it could be habitable. It's got light, it's got nutrients, it's got plants, but it's not making enough oxygen at a rate that's great enough that we can say for sure that it's not photolysis. So maybe it's habitable, but not detectable life. And I'm going to skip through this table where I did that calculation, and I basically tried calculating my net planetary biological production, which you see is on Earth, it's about 3. And on this water world, it's way less than 3. You could put this in terms of a sort of normalized detectability index, and there's basically orders of magnitude difference between the amount of oxygen that you would have as a flux on the water on Earth versus the water world. Desert planets. Okay, so if we have water worlds with way more water than Earth, then desert planets presumably have less water than Earth. How many of you have been to a desert? Everybody's pretty sure they know what life in the desert is going to look like? Does it look like this? You may not be expecting what you see when you go to an environment that you're not there all the time. This is Morocco. But there are other, and so we may not know whether places with a lot less water are habitable or not. We certainly weren't expecting goats in trees. They're eating the berries in the trees. That's why they're up there. Earth is actually probably as much a desert planet as it is a water world. Turns out our water is distributed and our deserts are distributed, and that's problematic because if you were to say on average what's the Earth, you can't really do that. Exoplanets are going to be part water and part desert too, maybe. We're really about 1/3 Desert, don't forget about Antarctica, that's why it's so big. They're warm and they're cold. They're highly weathered and oxidized, which makes them a little more like Mars. And they're inhabited, maybe by goats and trees, but maybe by these. So this is my favorite layered ecosystem. This is a desert soil crust. It's a cyanobacterial mat on the surface of a dry soil that's mostly quartz sand. Quartz sand is abysmal substrate for a living organism. Let's just all agree to that. But in this millimeter scale layer on the top, and you can kind of see that there's a layer. There are photosynthetic organisms, nitrogen fixers, heterotrophs. Because we can fix carbon and nitrogen, we solved some of our metabolic problems. And it turns out they also do some fairly fancy machinations to deal with phosphorus. They have uptake and retention systems that involve small acids and enzymes. They store it in their biomass. And they have really important metal requirements to run the enzymes that do all this in a millimeter. It's awesome. And if you run microelectrode profiles, you get the same kinds of distributions that Ken Nielsen showed us at the millimeter scale. So I like my gradients squished together when I can find them that way. The problem is the water, right? That desert, it's a pretty wet desert. It's 10 inches of rain a year or so. It's outside of Phoenix. But much of desert planets and some deserts on Earth are much drier than that. This is the Atacama. My student was up there. This is Donnie. He was in that picture. He put in these data loggers that measure temperature and humidity. Can you see these lines, more or less? Okay, good. We measured temperature and relative humidity at different depths in the soil column. What we see is that there's a strong diurnal temperature cycle. Gets damped out as you go down because it's hot at the surface and colder at the bottom, and that changes over the course of the day. But the relative humidity, this light blue line, is fairly stable. Well, if you have stable relative humidity and a temperature gradient, you can calculate absolute humidity because relative humidity is a normalized water vapor content. Absolute humidity has this big diurnal cycle. And I drew those in solid in case you couldn't see them from the back, but it worked out okay. And this cycle in absolute humidity may actually constitute a daily water cycle in the Atacama soils. How much water is it is the real question. And so here I've zoomed in on one of the absolute humidity curves. And what we think is happening here is something called water vapor absorption. So when the absolute humidity is low, the water vapor, these are little water molecules, are all absorbed to the surfaces of the soil. You can't measure them in the vapor phase, so there's no humidity to detect. When the absolute humidity is high, that water vapor is desorbed and it's in the vapor phase in the soil pores. And at the other side of the day, it does this. And you can calculate the volume of water this corresponds to, and it's something like a couple tenths of a millimeter of water. Compared to the 2 millimeters a year, that's not so bad. There are places where people have shown that water vapor absorption is enough to run metabolism. Now, the place where there's data for that is up by Flagstaff, Arizona, and it's a semi-arid environment. It's fine. We don't know if water vapor absorption is enough to induce microbial activity in the Atacama, but it's really small when you calculate it. And in point of fact, they've calculated it for Mars based on the data from the Curiosity rover, and there's more water vapor absorption on Mars than there is in the Atacama soils. We can talk about why that might be an overestimate, but that's okay. But it does suggest the Atacama might be at some limit for habitability. But there are cells, we know that. There is 1 or 2 papers that suggest evidence for microbial activity in the Atacama, but it's very difficult to measure. This whole project started because we went out to measure metabolic fluxes and we got zip. So we used our temperature and humidity data. The last story is about weird planets. And I was set up beautifully for this story by Kevin because really this is a story about ocean worlds. And I'm going to go out on a limb and say that we can use the beautiful Enceladus plume chemistry data from Cassini, even with its 1980s era mass spectrometer. Turns out mass spectrometers are beautifully mechanical. But we can actually do geochemistry from this data. And if you ask the average geologist, please tell me what the geology of a planet is, and all I'm going to give you is organic compounds of less than 4 carbons. The average geologist will run screaming from the room. First off, they haven't taken organic chemistry, and second off, organic chemists don't tend to think about temperature and pH as controlling factors for what's going on all the time, unless they're adding like swimming pools of sulfuric acid to a reaction to make it go. So these are the compounds that they found, and you don't need to recognize any of them. And I've highlighted a few that I'm going to talk about in a minute. The biggest problem we have right now is that the quantification of how much of these compounds are present in the plume is not as good as we'd like it to be. But in the future missions to future plumes are going to give us better concentration data, and so that's going to be great. But remember, I'm unintimidated by the lack of data. The Hydrothermal Organic Geochemistry group at ASU is working on this thing we like to call the Habulator, the Habitability Calculator. And what it does is it's going to take input in the form of organic compound data from planetary measurements. It's going to feed it into the Habulator, and it's going to spit out temperature, pH, and redox state of the environment that those compounds came from. We're going to do geology from organic chemistry, and we do it because we do experiments to measure mechanisms and rates of organic compounds in hydrothermal systems. We have knowledge gained from the modeling of Earth systems, and the better those models get, the more knowledge we have. And we have a strong component of thermodynamical data and predictions that allow us to put things in terms of temperature, pH, and redox conditions. So how do we do it? A reaction quotient is the products of a reaction divided by the reactants of a reaction. And this happens to be acetic acid and acetamide. Those are two compounds that were measured, or two compounds that are consistent with things that were detected in the Cassini data. That equilibrium between the acetamide and the acetic acid requires the addition of ammonia, and it has a log K, an equilibrium constant, as a function of temperature that looks like this. So it's pretty good at low temperature, and it's smaller at high temperatures. I wouldn't be a good organic chemist if I didn't tell you it's slightly more complicated because both of these species can exchange a proton. And so there's also a pK-pH relationship for all those reactants and products, and they look like this. And if you combine all of them, you can calculate an apparent Q, essentially how favorable is this reaction, as a function of temperature and pH. And what you see is there's a maximum here at high temperatures and relatively neutral pHs. Cool. So if you knew the concentrations of the two species were good, you could ask whether or not the temperature of the system, was consistent with equilibrium. Or if you assume it's at equilibrium, it'll tell you what temperature you're at. Well, you've got one reaction, you get one of these phase spaces. If you have three reactions, you can determine three of these phase spaces. And all of these molecules, except for this dimethamine, are molecules that were present in that Cassini data. Well, they have different temperature pH spaces. That's cool. If we had concentration data, so we could calculate actual Q, we could constrain the temperatures and pHs that those concentrations that we measure, the actual presence of the compounds, dictates. So here's the one I just showed you. Here's another one for this reaction. Here's one for this reaction. If all these reactions are happening together and there is equilibrium, then the overlap of all of those values for Q, the favorability of the reaction, will tell you the temperature and pH consistent with the equilibrium of all those things. Well, now suddenly, assuming that this hypothetical data, kind of like modeled spectra, says that this ocean has a temperature, it equilibrated at some point at a temperature somewhere around 100 to 150 degrees C at a pH of something like 8 to 10. So that's cool. That's a lot of geochemical information from a bunch of small organic compounds. The reality is, data's coming, and we have to be ready for it. We have to be able to do something with this data. So we're going to do more experiments and more modeling, and there's going to be a lander or another mission to these moons, and we're going to be able to tell you something about the geochemistry. So takeaway messages for this talk, and you've seen them already. Phosphorus and nitrogen are critical for biogeochemistry in many different environments. And we know almost nothing about them in stars, and so it can be very hard to predict how much there's going to be in planets. And so for all of you stellar abundance observer types, please go out and measure phosphorus, please. Biogeochemistry on planets with more water than Earth and with less water than Earth could be very different from the biogeochemistry on our own planet, and the geophysics coupled to the biology can make that harder. We need models that do both geophysics and biogeochemistry. And lastly, we have to get creative about how we're going to get geochemical information from the data we get. And the story about, not a story, it's a model called the Habitability, about how we're going to predict temperature, pH, and redox from equilibrium among organic species is one way to think about that. Because eventually, for exoplanets, the data is coming. And that's my story.
Thank you. We have time for probably 2, maybe 3 questions if they're fast. I see a hand in the middle there. And we'll go ahead and start there. Oh, sorry, you wait for the mic. Just over here. Sorry about that. Thanks.
Sorry about that. Yeah, that was an excellent talk. I had a question about actually the assumption of equilibrium for the Habitability. How likely is that to be a valid assumption?
So whether the assumption of equilibrium is a valid one or not is important. The more reactions that we can feed into the thing, the better, because some of them will be at equilibrium, and some of them are going to be far away from equilibrium. And in fact, those things that are way far from equilibrium are going to tell us about energy sources that are available in that system, right? If an organic compound is way out of equilibrium, it's food. And so that's a plus, but you're right. We actually, to make this work well, you need way more than 3 reactions. So it's a preponderance of the data thing. And if there's hydrothermal systems, there's reason to suspect that they at least equilibrated at high temperature at some point. How that will translate into what we see in the plume needs work.
Next question in blue.
We're focusing so much on water in these cases, but what about planet
like Titan? That's a perfectly fair question. We don't have places on Earth where we can do experiments to look at geochemical variation and biogeochemical variation for things like Titan. But the Habitability was set up for plumes of water from oceans. If you can get small organic compounds in an atmosphere, you could begin to do the same sort of thing with that data. Now, the assumptions of equilibrium in atmospheres, I've learned when I'm talking to astrophysicists, everybody assumes the atmosphere is at equilibrium. When I'm talking to geophysicists, everybody's like, well, why do we assume that? And so we need to build this conversation and figure out where do we start. This gets back to the what theory do we actually need to work from. But you should be able to do similar kinds of equilibrium calculations to assess what's in equilibrium and what's not for, say, a Titan atmosphere or a Titan lake if we had Titan lake data.
What other questions do you have? Mike?
Thanks. I'm absolutely convinced that phosphorus is super important for life and, very limiting aspect. But you have P and nitrogen. And so I might have missed the part where you spoke about nitrogen.
I glossed over the nitrogen because this talk was too long to begin with. Nitrogen is equally important. And you'll notice that many of the Cassini compounds have carbon and nitrogen in them. And nitrogen reactivity is something we can actually do in the lab experimentally. From a biology perspective, I do make the tacit assumption that biology has solved a nitrogen problem. If you have an N2 atmosphere, you can run biology because you can fix nitrogen and make ammonia. We also have a whole lot more data for nitrogen than we do in the stars. The other presumption that I glossed over is that when we look at that red field ratio of C to N to P, nitrogen's not the limiting nutrient. You will almost always have enough nitrogen to do what you need to do. And so from an understanding reaction equilibrium and reaction kinetics, it's that limiting nutrient that is the one you have to kind of get a handle on. So I actually started out as a denitrification person. I like nitrogen, but I was trying to sell a phosphorus story.
Thank you. Let's thank all of the speakers in the morning session again.